Hi everybody. Problem number 8 on the Thermodynamics and Chemistry 1 worksheet. This one asks us to calculate the delta H, the enthalpy for this reaction. Change in entropy for the given, enthalpy for the given reaction. And the reaction is given to us here. It's the reaction of solid sodium hydroxide with hydrochloric acid gas to provide sodium chloride solid and water vapor. Now, a couple things before we get started. All the information on the slide right now was provided in the problem, and I wrote it down in exactly the way that it was written down. So I want to point something out. When you're doing these problems, you need to be especially cognizant of the physical states that are listed here. Different physical states will have different thermodynamic values when you look them up in the tables in your textbook or online. So pay attention, for instance, that this is water vapor at the end. It's not liquid water or solid water. Sodium chloride and sodium hydroxide are both solids. They're not dissolved in water. Hydrochloric acid here is a gas. It's not dissolved. It's not anything else. So pay attention to those physical states. When you go and look up thermodynamic numbers, provided they maybe weren't given in a table in the problem, when you go and look those up in your textbook or in an engineering chemistry handbook, you're going to find numbers like this. And when I looked these numbers up, because I wanted to double check that the problem was correct, it turns out that the numbers they gave us here don't have units of kilojoules like they listed. The units are actually kilojoules per mole. And that is by far the more common way you're going to find them is as kilojoules per mole. So the reason I want to point that out is because the way that the solution is shown for this problem on the worksheet is not probably the best way to think about it. So let me explain. Anytime that we're going to calculate an enthalpy change, all right, and in this case it's standard state, so we can put that little subscript 0 there, it's going to be the sum of all of the enthalpies of formation of the products minus the enthalpies of formation of the reactants. Okay, always products minus reactants. And so in this case, when we look at what that means, it means that I have 1 mole of sodium chloride as a product, solid. I'm omitting the physical states down below just because it's a little bit messy, so you see them up above. I also have 1 mole of water vapor, and I'm subtracting 1 mole of sodium hydroxide, and I'm subtracting 1 mole of HCl. Now, the reason that I don't exactly like the way this problem solution is written in the answer key is because they ignore that mole part. And the reason they're allowed to do that here is because the stoichiometric coefficients, the balance coefficients in this reaction are all 1s. I have 1 mole of sodium hydroxide reacting with 1 mole of HCl to produce 1 mole each of those two products. What I wanted to point out here is that the numbers in your table are kilojoules per mole. And so if you had a different reaction maybe that had a coefficient of a 2 or a 3 somewhere, you would have to multiply that energy quantity by that coefficient to get units of kilojoules. All right, our final answer here is going to have units of kilojoules. So in this case, it's okay to just use the numbers out of the table as they're written with units of kilojoules, but keep in mind what I'm really doing as I'm saying here for NaCl, for instance, that I have 1 mole of that stuff times a negative 411.2 kilojoules per mole. Okay? If I had 2 moles there, that quantity obviously would be doubled. I have 2 moles times negative 411.2. All right? I'm going to omit the moles part because these are all 1s and I just don't want to crowd up my calculation, but know that that's how you would do it. All right, I'm adding here now the heat of formation, standard heat of formation of water vapor. I get a negative 241.8. And now I'm subtracting Sodium hydroxide is a negative 425.6. And subtracting again, HCl vapor is a negative 92.3. All right, be very careful with your signs here, right? I'm adding together my products. So those are both, in this case, going to be negative numbers, but I'm adding them together. And then I am subtracting right there my products. The way I wrote it, I said subtract one product and subtract the other, or sorry, subtract one reactant and subtract the other. Sometimes you'll see a book say to subtract the quantity. However you write it mathematically, just make sure that you are being careful with your signs. All right, so in my little calculator, I'm going to type in my negative 411.2 to start with. Then I'll be adding on that negative 241.8. And then I'll be subtracting a negative 425.6 and subtracting a negative 92.3. So altogether, I get a number that's still negative, and it's negative by 135.1 kilojoules. Okay, that's my change in enthalpy for this reaction. And essentially I did it by looking up the enthalpy of formation of each piece, figuring out essentially what it means to break apart my starting materials and reassemble them as products. Okay, this is really great because enthalpy is what we call a state function. It doesn't matter what path you take to get to where you're going, as long as you get to the same spot. And so this is one way to do it, which is great. If I had different information, perhaps other reactions that I already know the enthalpy change for, then I could use those. That process is called Hess's law, and that's what we're going to be looking at in the next video in problem number 9. So this is an example of using the thermodynamic values, the enthalpies of formation, and it's always going to be here, the total of your product's enthalpy of formation, subtract the total of your reactants. Units are typically going to be in kilojoules. All right, those values are typically going to be found either in a problem, if it's a problem on a standardized test, or in a homework, something like that. If you're looking at a particular textbook, they might be given in a small table in the text, within the chapter, like an excerpt table that gives you all the relevant numbers. But typically at the back of that textbook, there's going to be an appendix. If you're looking at the OpenStax textbook, for instance, in the current version, that's Appendix G. That could change, of course, with different versions, depending on when you're looking at this video. But you can go and find all the thermodynamic numbers you need, and these are enthalpies of formation. All right, problem 9 comes up in another video. We'll look at Hess's law in that one. But for now, have a great day.